you for staying here on Friday afternoon. My talk is slightly different from the abstract that you can see in the program, but still the title is the same. And this is a work that I have to thank a lot of people that has been working with me in the last few years, including the ICTR collaboration. Now, more or less, this is the structure of my talk. I will start with a question which is not so well defined, but I try to define it during the talk. And my question is, to what extent can we say that the statistical property of the inertial range are somehow universal with respect to the dissipation mechanism in homogeneous and isotropic turbulence? Of course, you can raise questions about what is the relevance of the structures, the vortices, whether or not there is any Reynolds dependency in the intermittent that we measure, or some other question that in any case relate to the non-universality of the inertial range statistics. We have an answer for this question for the case of homogeneous and isotropic passive scalar. And that answer is positive. I mean, whatever mechanism you put at the end of the inertial range to dissipate, then the intermittency is universal. However, the passive scalar and the Navier-Stokes equation are different, so from time to time you see there are questions about this problem that came out in the literature as well as in the talk, and I want to give some remarks on this point. How to do that? My approach is to look at what we can get from experimental and numerical data, and in particular from Lagrangian dynamics. And the reason why I will focus on Lagrangian dynamics, because it turns out that the Lagrangian dynamics is a real very good tool to look deep into the dissipation range. And this is somehow more difficult when you do it in the Eulerian frame. Then I will give you some, let's say, theoretical consideration and some conclusion, hopefully. Okay. The first thing that you observe in a Lagrangian trajectory is something like this. There is a particle, a tracer, which goes around in the system, and at a certain point it is trapped in a vortex. Of course, when it's trapped in such a kind of structure, you see a strong oscillation in the velocity, and as a matter of fact, you also see a very large acceleration effect. So you see, if you are looking at the Lagrangian dynamics, the most important thing that this guy can do is to fill this structure in the system. And of course, this is an important information because the Lagrangian can really give you information about these structures. One of the outcomes of the vortex trapping is that if you look at the tracer, which is this black line here, you see that the PDF, the acceleration of the PDF of the acceleration divided by its root mean square. This is a picture that you have seen many times during this meeting, but I mean, the PDF is very, very intermittent. Actually, I think it is the most intermittent quantity that you observe in any turbulent flow. So, I mean, from a point of view of working in intermittency, one has to care about how can we understand this intermittent from what we know from the inertial range.
How is number ST defined?
Sorry?
Number ST, how is it defined?
ST is the Stokes number, which is the ratio between the typical the relaxation time of the particle and the typical relaxation time of the flow. But I will not consider all the other color curves which refers to Stokes number which increase. I only want to focus on this tracer, okay? Now, you have seen yesterday morning the talk by Luca Biferale, and this is one summary of what he told us. I mean, you can measure the structure function in the Eulerian frame, you can measure the structure function in the Lagrangian frame, and then if you take it seriously, that the Euler equation, which are supposed to be the most important thing in inertial range, satisfy the invariance condition that is written here, then you should relate the characteristic fluctuation of intermittency in the Lagrangian frame to that of the Eulerian frame. In other words, you can make prediction, if you wish, what we know from the Eulerian structure function from what we could know from the Lagrangian structure function. Please, I note that I'm telling you that I trust this relation not just because of dimensional analysis, but because this is an invariant transformation of the Euler equation. Of course, there are problems with the Lagrangian structure function as well with the Eulerian, in the sense that the transverse and longitudinal structure function looks like different so far, and all the things that has been told by Biferale can be applied also in this case. Now, one of the things that you observe in the structure function of the Lagrangian trajectory is that, okay, there is the inertial range. I will show you a better graph of that, but this is just a cartoon at low resolution of a numerical simulation in which you see the green line, which starts from the inertial range, okay, then there is this dip here, and then it goes to value of 2, as it should be when you look at the slope. This is a measurement. So when you look at the slope of the fourth to the second order structure function. Now, in order to understand why you have such an increase of intermittency, which correspond roughly to the dissipation range, one can play the simple game to put heavy or light particle in the system, and you observe that those guys, which are usually outside vortices, doesn't show such an increase of intermittency. Why? The light particles, which are deep inside the vortice, have an intermittency which is much larger. So the first qualitative understanding of this picture is that the intermittency that you observe in the inertial range is somehow related to the existence of this structure. As I said, that was a cartoon. Recently, as was shown by Luca, there was an intensive collaboration among all the people that are currently working in the experiment or in the numerical simulation of Lagrangian particles. And this is what they obtained, what we obtained. That was already shown by Luca. You see that there is a very nice scaling region in the inertial range, almost 1 decade. But then everybody got almost the same results when they go into the dissipation range. So this is a very robust feature, as well as the scaling, and this feature should be related to the existence of vortices in the dissipation range. Now let me go on. It was mentioned by Srinivasa in his lecture that there is one thing that looks like a miracle, which is the refined Kolmogorov similarity. Now, the refined Kolmogorov similarity tells us that the energy dissipation and the velocity fluctuation should be related. Now, again, if you trust the similarity law in the Navier-Stokes equation, this one, which is an exact similarity law, then it is indeed true that you would expect that the energy dissipation, the fluctuation of this quantity, should be related somehow to the fluctuation of the velocity field. Now, in the Lagrangian framework, such relationship can be translated in this way, and you can check whether or not this is true by using the standard analysis that has been done so far for the refined Kolmogorov similarity. Now, this is the result. So this is the refined Kolmogorov similarity in the Lagrangian frame. That is done with the numerical simulation up to 2048 cube. So it's very well resolved. And these are three lines which refer to three different ways to compare the Lagrangian refined Kolmogorov similarity. The blue lines refer to this quantity equal to 1. So we just look at this ratio to understand how it grows. And indeed, it grows very fast. The second one, the red one, represents the case when we use the energy dissipation along the trajectory. And you can see that more or less it is a constant, and then it grows. There is a small dip here, and then it grows. The third one, the green line, refers to the case in which instead of using the energy dissipation, we use the vorticity. And you see that this is not very well verified. Okay, there is a big dip here, and then it goes up. But eventually, it is not as constant as the energy dissipation. So this is a conclusion which compares very well what has been obtained recently by Srinivas and other people working in the Eulerian frame. And this is the first observation in the Lagrangian frame of the refined Kolmogorov similarity. Again, if you look at different particles with different, if you look at the tracer, you get this curve, the black ones. If you look at the particles which are with different inertia, you see that most of, in the inertial range there is no deviation, but then when you go into the dissipation range, you see a large deviation, a jump, which depends whether or not the particle is trapped or not trapped in the vortex. So this is an observation that the Lagrangian similarity, the refined Kolmogorov similarity works very well, but eventually the effect of the vortex here near the dissipation range destroy this effect, and you see that there are different results with respect to different inertia of the system. Let's go on and let us push our question slightly in a better way. Okay, the question is, what we have observed so far is consistent with respect to what we understand of intermittency in the inertial range? This is the physical question. Technically, you can say, well, let us understand whether our approach to describe turbulence in the inertial range is consistent with the intermittency we observe in the dissipation range, which means let us understand whether the multifractal description is able to give us the same information. Now, start with the acceleration. Again, multifractal is a statement of the symmetry of the equation of motion. By using the idea of Frisch-Vergasola that was used also for gradients and was illustrated so clearly by Srini in his lecture, you start saying that there are not a dissipation scale, but the dissipation scale must fluctuate with respect to the velocity at the local level. So you have a prediction of what is the fluctuation of the dissipation scale. You take this prediction inside the velocity difference at a given time, and then you can predict what is the acceleration. Now, after a huge but simple computation, you end up with a formula which is this. You should trust this formula because it takes about 1 hour to get it out from all the mass of the multifractal. You take this formula and you obtain this line, which is here, represented with the acceleration of the tracer. This dashed line here is the Kolmogorov prediction. So the first information that we get is that by using the idea of a fluctuating scale in the dissipation and the multifractal description, we are able to explain the strong intermittency in the acceleration, despite the fact that, as I show you, Therefore, the particles are trapped in these vortices. Then you do the same game with the Eulerian structure function. You can start from a proposal by Manevaux for the Eulerian framework that has been rewritten for the Lagrangian framework, in which the idea is that you make essentially a smoothing of the multifractal stuff by using a kind of Bachelor parametrization for the multifractal field. Let's forget about the detail. The idea is always the same. You put fluctuating scale into the system, and you try to understand whether or not this is enough to explain the observed behavior. Those band here represent what you get from the formula, and this is for the longitudinal and transverse structure function in the Eulerian frame. And you see that the multifractal agrees very well with the behavior that you can get from the data. So this is not trivial, and it's indeed one of the results that has been published in the paper that I was mentioning you before. So we can reach some preliminary conclusion, which is the following. It's certainly true that the vortices are linked to the dip in the local slope of the function, of the structure function. No way. It is certainly true that the multifractal plus the idea of a fluctuation in the dissipative scale is consistent with the data. So you see, linked and consistent are mild words. You can choose whatever you want. The question I have in mind is, which is the effect of which? In other words, are vortices the quantity which in some sense fix the intermittency in the inertial range, or the symmetries of the equation of motion are in some sense fixing the existence of the vortices? Okay? It's not very well-defined question. I hope to clarify it in the future, but again, the feeling is that if the vortices are dominating also for the statistical property of the inertial range, then you may think that the behavior of these structures here may affect strongly what you observe in the inertial range, and therefore there may not be universality in the intermittency of the inertial range as well. Now, this is for the Lagrangian structure function, and you find the same effect for the Eulerian structure function. Here the figure is not so good, but you can trust when I say that this dip is slightly smaller, but you still see it in Eulerian structure function if the Eulerian structure function are very well resolved. So this is the question that I want to understand. So in order to understand this question, or at least to make a step in understanding this question, I want to make a simple case. I took the most stupid model I know, which is the shell model. The shell model is a dynamical system which has the scale invariants that I want to use, nothing else. So it's a dynamical system with a scale invariant. The shell model has scaling property. The scaling properties are anomalous in the sense that we're speaking about. And I want to understand whether this model, which is actually the way in which I can produce a multifractal system without using the equation of motion, has something to say about those information on the dissipation range. Now, why I expect some information from the shell model? Well, the reason is that certainly it is observed this anomalous scaling in the structure function. Moreover, we know from balancing the terms in the equation of motion that the structure in the dissipation range should be like this. So you see, again, there is a fluctuating quantity of the dissipation range, but when Kn becomes very large, these terms goes like Kn, and therefore you expect for that in the dissipation range you should recover exactly what you observe in the non-anomalous case. So therefore, this quantity must go to P over 2. Okay? So what I did was a set of numerical simulation when I was using the shell model, and those figures refer to different Reynolds number. Of course, in the shell model, it's very simple to increase the shell number, the Reynolds number. So I am going from 10 to the 4 to 10 to the 8. And you observe a few things. The first thing is that there is a bottleneck or a dip, okay? And the dip is there. I mean, exactly as you can observe in the Lagrange abstraction function. The second thing is that the dip is increasing when the Reynolds numbers increase. So you have something which is changing like the log of the Reynolds number. This is K, and this is this quantity. So by increasing the Reynolds number, I'm increasing the dissipation scale in K space. And the fact that this guy is going down means that I have something which is changing as a function of the log of Reynolds number. This is true for the 4th order or for the 6th order, I mean, any order. The other thing that it's interesting to observe is that the first thing that the shell model does at very low Reynolds number is just to build up the dip, okay? So in some sense, the first thing that happens in the system like this, where you have a multifractal behavior, is to set up the gradients, which was the observation referring to the paper by Jakob, Srinivasan, and Schumacher on the starting of the gradient when you have a low Reynolds number. So these are three interesting features which are somehow observed also in the numerical simulation of the real Navier-Stokes equation. Needless to say, when I go from, when I use the multifractal formula, I get exactly the same results. You see this line here is just a line that I'm drawing by hand to show you how it increased the dip when it increased the Reynolds number. This is exactly the same line that I have here without changing, and this is what you get from the multifractal prediction. So this is a shell model, this is the analytical prediction, and you can see that the agreement is very good. Now, once you have done this piece of work, I would be tempted to reach the following conclusion. The first is that in the dissipation range, what you observe is what you should predict from the multifractal. In other words, the dip, the probability distribution of the acceleration, also the offset of the Lagrangian refined Kolmogorov similarity hypothesis. I will not show that, but also the offset can be predicted by the multifractal approach. Now, the second thing is that everything goes like the log of Reynolds, so this is not something surprising. The third thing is that all this picture together suggests me that what's happening in the dissipation range will not change the statistical property of the inertial range at very large Reynolds number. So this is my conclusion. The other conclusion that I want to stress is that when we speak about the multifractal approach, I'm not speaking about any multiplicative process or any particular kind of fitting. I'm saying that we have a formalism in which, if you know what is this function d of h that you use in the multifractal theory, then you should be able from that function to compute what you want to compute for homogeneous and isotropic turbulence as far as homogeneous and isotropic quantities are considered. Of course, our d of h, the d of h is not known in the sense that it is not known from first principle. We can compute it for the passive scalar. We are not still able to compute it for the Navier-Stokes equation. We are almost computed for the shell model, okay? But it's something that you can obtain from the data as information. Once you have it, then you can connect all the other information. Now, this is non-trivial, absolutely non-trivial, And I think that in understanding what we observe, at least in homogeneous and isotropic turbulence, we should also refer to what kind of, by quote, prediction you can make by using this approach. I thank you for your patience.
Question, Roberto, the last conclusion you have, does it come essentially from shell model analysis?
Well, it comes from the fact, let me say, you see, my question is, I don't know if it was clear, but my question is, it is clear that in real turbulence you have vortices, no way out, okay? You observe the effect of vortices here. Now, this means that the physics of vortex, reconnection, interaction, whatever it is the dominant features also with respect to the inertial range. This was the question. Now, the fact that the multifractal, let's forget about the shell model. Shell model is a way to do the multifractal not by fitting parameters, if you wish. The fact that the multifractal gives you exactly the same stuff without doing anything means that this feature is there anyway and can be predicted from your knowledge of the inertial range. I mean, if you give me the fluctuation on the inertial range, I can predict this. And this is inside the multifractal. It's not outside. Now, because of that, it is difficult to believe that vortices can change the dynamics in the inertial range. This is my preliminary conclusion.
My point was you're inverting the statement more or less. And
well, that is a semantic problem.
yeah.
This is a semantic problem, but of course.
It's more than semantics. Maybe more than semantics. But
No, I think it's a semantic problem. You see, because the point is the following. The degree of intermittency in the inertial range can be quantified. The degree of intermittency in the dissipation range can be quantified. Okay? If you can go from one to the other in a well-defined way,
you see?
then it's difficult. Huh?
Okay, I got the answer.
Okay.
One more.
Can you be sure that the inertial
I
range?
cannot hear you.
Can you be sure that the inertial range is at
There's no way. It's my fault, don't worry.
You shout.
fine? Can you be sure that the inertial range is at 10 tau eta and higher, not in some other region, lower, shorter time scales?
Well, for this particular, okay, for this
repeat the question.
the question is whether we are sure that the dissipation range is here. Okay.
Yeah, for the
Okay.
Lagrangian.
Now, in this case, it was just if it is 10, 5, or 15, I don't know. I mean, it's order 10 anyway. In this case, it's sitting here, which is about 2. The inertial range more or less starts at order 20 with respect to R. If you use this kind of measurement, it starts around 10. But I mean, it's small deviation. You see, when you have resolution of 2048 cube, you don't care very much if it's 10, 20. It was a problem 25 years ago when you had to reach only 128 cube in the numerical simulation.